Okay, guys. Well, let's see. We got to quantum mechanical model at the end of the period. We were starting to watch the video with Scott again. We'll come back to that video on Monday and a few other simulation type things as well that I won't be able to do since we're not in person. But the quantum mechanical model of the atom is our current model of the atom. So when we said, we've known for over almost 100 years, are we over 100 years now? Yeah, I think we're over 100 years now that we've known that the Bohr model is incorrect. This is the quantum mechanical model was what developed following that, and we've been building this model ever since. And it's been built for quite a long time. We're still fine-tuning things, certainly, but we're still working underneath the same model today. And so in the quantum mechanical model, it's a little bit different. Electrons do not follow orbits, so they don't follow these nice circular paths around the nucleus. And a wave function actually describes an electron's possible positions in three-dimensional space, and it's often called an orbital. So instead of a shell, we refer to them as orbitals. And again, it's a wave function. It's an equation that describes a wave and the probability of finding an electron in a given area. And again, we'll give you some visuals of this on Monday. I think that will help quite a bit if you're struggling to see it. But if you think back to the video of Scott with the slinky and he was starting to sketch out those different shapes that the waves make as they go through that slinky. That's kind of what we're talking about here. And again, we'll give you some more visuals. We'll give you some visuals certainly in the PowerPoint here, but we'll give you some more visuals on Monday. And so possible wave functions include what we call 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 6s, 6p, 6d, 6f, 7s, 7p, 7d, and 7f orbitals. So there's lots of possible wave functions here, and they have slightly different shapes and different amounts of energy, but every electron under one of these labels in a given atom is at the same quantized energy level. And so in other words, any electron that's in, let's say, the 2p wave function, any electrons that are in that 2p wave function will have the same energy level. And again, that's a quantized energy level, meaning that these electrons can have certain amounts of energy that put them into this 1s wave function or 2s or 2p, but that's it. There's nothing in between. So it's one of these options and that's it. So what is an orbital? So we said a wave function describes the electron's possible position in three-dimensional space, and we call that wave function an orbital. So an orbital really is just a graphical representation of the space that an electron will occupy 90% of the time. So 90% of the time, if we say an electron is in a 1s wave function or a 1s orbital, we're saying 90% of the time that electron is going to be located in this area. And again, we use a kind of a graphical representation to represent what that looks like in three-dimensional space. But it is a concept. It's not a physical structure. There's no physical structure there containing those electrons and keeping them within that certain space. And again, I think I've got some simulations for Monday that will really kind of clarify that. So we've got some images here to kind of help you, and we'll deal with some of the simpler ones, the 1s orbital and the 2p orbitals. I think are probably your easiest ones, and then they get a little more complicated from there. So if I look at the 1s orbital or the 1s sublevel, they sometimes refer to it as, that is again the location where the electron can be found majority of the time. Okay, and so you can see over here on the picture on the right at the top here, this dotted line represents the 1s sublevel. And again, this is three-dimensional, so it's kind of hard for me to represent here in two-dimensional space on your screen, but you can imagine this as an actual sphere instead of a circle, right? And so the electron's going to be within that dotted line 90% of the time. So you can see the other 10%, it's still pretty close, but it just extends out a little bit further than that. And so our 1s orbital or 1s sublevel, again, is where this dotted line is. It's actually a sphere in three-dimensional shape, and it represents where the electron can be found 90% of the time. Like every one of these dots is where the electron is at any given moment. And so you can see it's kind of bouncing around inside of there all over the place, and sometimes it is actually outside of what we would consider the 1s orbital, but majority of the time, 90% of the time, we would find it inside of that sphere. Okay. And again, no physical sphere is actually there. Okay. So a graphical, again, it's a graphical representation, is the area representing the area where the electron can be found 90% of the time. So typically we represent it just as a solid sphere, but again, there's no physical solid sphere there. Okay. The other one here, so that's the 1s. There's also a 2s. The 2s is very similar to the 1s. It's larger in size. There's a little bit of other differences with it that we'll talk about later, but then next we come to the 2p orbital. And the 2p orbital, actually there's three 2p orbitals. There's a p orbital in the x direction. There's a p orbital in the y direction, up and down. And then there's actually even a p orbital in the z direction, which is really hard for me to show you. That would be coming in and out of the page. Okay. So p orbitals have a little bit different shape. They're kind of like dumbbells, like there's one side here, and then there's a spot in the middle where there's nothing, and then there's one over here on this side. And again, this is similar to that second energy level that Scott showed us in the video, and with the slinky, where if you shake it hard enough, you get kind of these two spherical areas here on either side, and in the middle you get that area where there was kind of no vibration, right? And so this is kind of what they look like. And again, 90% of the time, if I have an electron in a 2p orbital, specifically in the x direction here, that electron 90% of the time is going to be in this area. And the same thing happens in the y direction. And again, there's a z1 coming in and out of the page, and the three of them together look really horrible. This is a horrible representation, but again, we'll give you a visual of this on Monday. If you can picture like balloons, and you can have two balloons side by side, and you can have one coming up above and one going down below, and then one coming towards you and one kind of going backwards. And we'll try and show you that visual again on Monday. Okay. So these orbitals fill up with electrons. And again, the electrons are attracted to the nucleus of the atom because of Coulomb's law, right? Just electrostatic attraction, opposite charges attract. The nucleus is positively charged and the electrons are negatively charged, and that electrostatic attraction is going to attract them together. And so electrons here, as we go across the periodic table, we're adding more protons, right? As we go across the rows and then down the row and across the row again, or down the column and across the row again. We keep adding more and more protons, and as long as those atoms are neutral and not ions, we're also adding more and more electrons here. And so those electrons are added to the lowest energy orbital that's available. And so they're going to fill that 1s orbital first before they start to fill the 2s orbital. And then they'll fill the 2s orbital before they'll fill the 2p orbital, again, based on kind of that energy level. And this is because nature always favors lower energy systems. It doesn't matter what we're talking about. Nature will always take us to the system that has the lowest energy in that system. So luckily there's a format that we can kind of follow to determine the lowest energy orbital available. And so that certainly makes it a lot easier having that pattern for us. So you work your way kind of from left to right, like you're reading a book, until you get to the element that you're looking for. An element's electron configuration contains every lower energy orbital and energy level that comes before it. The first number here, so like you're seeing this 1s1 over here, this is 2p1, 2p2, 2p3. The first number that's coming there in each of those boxes is called the principal quantum number. And the letter is telling you the type of orbital. Remember, we just talked about two types, the s orbital and the p orbital. And then the third one here, the power, that last number, the power, is the number of electrons within that subshell. Okay, so I've got the principal quantum number here is 2, and that has to do with the energy level. And then the orbital type is a p orbital. And specifically, the p orbitals have 2 electrons in them for the second one here, which would be carbon on the periodic table. Okay. So again, the important point here is electrons enter and fill the lowest energy orbital available. So the energy level of the subshell increases as you move across from left to right, and then increases again as you start the next row. So the top row of the D block is n equals 3. So if you notice here, this is referred to as the D block, this area where it's kind of sunk down on the periodic table where the transition elements are, or transition metals are. Okay. Note that here we're going 3p1, 3p2, 3p3, 3p4, 3p5, 3p6, and then we go to 4s1, 4s2, nothing abnormal there. But in this D block, once we hit this D block, then we're going 3d1, 3d2. So we kind of jump down to the third energy level again. Okay. Same thing happens down here when we get to the F1. It looks like these go in right here, and it looks like for those Fs, we should be either in 6 energy level or the 5th energy level, but in fact, we're in the 4th energy level. And so realize that there's kind of this weird trend that happens there. We definitely will talk more about why that is. But after the 6s is filled, you start filling, so after the 6s1, 6s2, then electrons start filling the 4f orbitals. And so 4f is at a higher energy than 6s is. Okay. So let's talk about that filling orbitals a little bit more. So hydrogen here has only 1 electron, has 1 proton. So if it's not an ion, if it's neutral, it will only have 1 electron. And that 1 electron will enter the 1s orbital. And so the electron configuration for hydrogen is 1s1. Again, the first number there is your principal quantum number. Your orbital type is s, and the number of electrons in that subshell is 1. Then going on to helium, helium has 2 protons, so as long as it's neutral, it'll have 2 electrons. They'll enter the 1s orbital as well. So this completes the n equals 1 energy level by filling the 1s orbital. So that 1s orbital can only have 2 electrons. So again, the principal quantum number here is 1, the orbital type is s, and the number of electrons in that subshell is going to be 2. Now, if I'm actually writing the electron configuration for helium, realize I would want to write 1s2. Okay, I don't need 1s1, 1s2. I just need the 1s2. Okay, because that's the same subshell. Then lithium now has 3 protons, so 3 electrons if it's neutral. 2 of them can go in that 1s orbital, but then that 1s orbital is considered full. That 1s orbital can't hold any more electrons. And so then that third electron must go to the 2s orbital, the next orbital, the next highest energy level orbital. And so the electron configuration for lithium would be 1s2, 2s1. So 2 electrons in the 1s subshell, and 1 electron in the 2s subshell. Another way of writing this electron configuration, because these sometimes get really long, is we can use an abbreviated form where in brackets we put the symbol for the noble gas that occurs before the row we're in. And so we're right now in the second row. So the noble gas from the first row is helium. And so basically it's saying take the electron configuration for helium and then let's just add 2s1 to that. And again, when we get to some more complicated ones, I think you'll see why that's very useful. Okay. So beryllium has 4 protons, so it has 4 electrons if it's neutral. 2, again, go into that 1s orbital. That's as many as the 1s orbital can hold. And then 2 will go in the 2s orbital. And so the electron configuration for beryllium is 1s2, 2s2. So again, this is showing us I've got 2 electrons in the 1s subshell and 2 electrons in the 2s subshell. Our abbreviated version of this, it's typically referred to as the noble gas configuration, is to put helium in brackets and then 2s2. And again, it's noble gas configuration because everything in that last column, group 18 on the periodic table, is a noble gas. So we refer to that as a noble gas notation. So you can see the filling orbitals for then boron, carbon, nitrogen, oxygen, fluorine, neon, and sodium there. And so again, each of these we're just adding one more. So once we get to the 2p sublevel, the 2p sublevel can hold 6 electrons. And so we've got 1s2, 2s2, 2p1 for boron, has 5 electrons. Carbon's going to have 6 electrons, so 2 go in the 1s sublevel. 2 go in the 2s sublevel, and then 2 will go in the 2p sublevel. And again, p orbitals can actually hold 6 electrons because each one of the px can hold 2, the py can hold 2, the pz can hold 2, and so total that's 6. And so nitrogen here, we're going to continue to add electrons to the p sublevel. And so we've got 2 electrons in the 1s sublevel, 2 electrons in the 2s sublevel, and then now 3 electrons in the 2p sublevel. Oxygen, another one goes into the 2p sublevel. Fluorine, another one goes into the 2p sublevel. And then neon, our 6th one, goes in the 2p sublevel. And now we're full. That p sublevel is full. So as we go to sodium, and we need to add one more electron now we go to the 3s sublevel. Okay. And again, notice how that noble gas configuration goes. For boron through fluorine, it's all helium, and all we need is just the second quantum numbers, so the 2s2, the 2p1, 2s2, 2p2, all of those added on to the noble gas in brackets. And again, with neon, the second energy level is full with neon. And so we don't use noble gas configuration for noble gas for obvious reasons. So sodium there, again, now our noble gas is again the noble gas in the row before, which would be the second row. It would be neon now in this case, and then we would just have to include anything with a quantum number of 3, in this case 3s1. Okay, a couple kind of examples here. This is, notice that in scandium and samarium, 3D comes after 4s, and 4F comes after 6S. So again, we kind of have a filling order that you can kind of follow on the periodic table. Let me check and see. Yeah, I think we're definitely going to come to talking about the blocks on the periodic table, the S block, the P block, the D block, and the F block. And when we talk about those, I think that'll help make that a little clearer. So I'm kind of looking here. I think what we're going to do is, because this is new for some of you, I want to stop here. And I'm going to have you do a POGL today. So kind of a change in plans again. Sorry about that. There is a really good POGL activity that helps with this filling orbitals and the order that we fill these orbitals in. And so I'm going to have the sub give you that handout, and you can work on that in your groups, obviously. I will I'll put an answer key on Power Learning for that POGL, with the understanding that you're going to really try and give it your honest, full effort to do that in your groups without looking at the answers first, so that you can understand it better. And then if you really get stuck, you'll have the answer key to go to. And don't worry about wording on things. So if you're like, well, I know I'm right, but I don't know if I'm wording it quite correctly, don't worry about that piece as much. We're really just focused on, are you understanding the filling orbitals, and are you able to answer the questions that are there. And again, if you get stuck there, then go ahead and go to the answer key. Once you're all the way done, obviously go to the answer key, and you can kind of check your answers. And so let's do this. Let's do that in class. If you don't finish it, let's finish it up for homework. You can do a summary on the part that we've done so far for lecture 1.5, and you can do the problems from the worksheet that are related to 1.5 for homework. It certainly will not be all of them. I'll give you some more direction in Power Learning in terms of which ones specifically you can try over the weekend. And then let's call that good, because I want to come back and watch some more of Scott's video clip. There's a couple computer simulations I want to show you with this. And again, I think this is a really difficult concept for you to get the first time. And I know a couple of you have seen it before, but I would rather be here as we're going through the rest of the notes here. So have a great weekend, and make sure you